So in this video, we are going to look at the exponential form of a complex number and how to find the nth roots of a complex number. So the Maclaurin series expansion of the natural exponential function, that is e to the power x, is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x exponent 4 over 4 factorial plus x exponent 5 over 5 factorial, and so on and so forth. Now let's call this equation 1. At this point, we are going to replace x in equation 1 by j theta, that is the imaginary value. So let x equals j theta. In that case, we have e exponent j theta equals 1 plus j theta plus j theta all square divided by 2 factorial plus j theta all cube divided by 3 factorial plus j theta all exponent 4 divided by 4 factorial plus j theta all exponent 5 divided by 5 factorial, and so on and so forth. Now in the previous video, we learned how to simplify the powers of j. We said that j is equal to the square root of -1. In that case, we have j squared to be equal to, you want to square this so that you have -1. J cube is equal to negative j exponent 4 is equal to 1. And then for j exponent 5, you have j exponent 4 times j exponent 1. Now if j exponent 4 is equal to 1, then 1 times j is still j. Therefore, j exponent 5 is the same as j. Now let's continue to simplify this equation. So e exponent j theta is equal to 1 plus j theta plus, this time we are going to have j exponent 2. So j exponent 2 is the same as -1. So we are going to have negative theta square divided by 2 factorial. Next we have j exponent 3, which is negative j. So this becomes negative j theta exponent 3 divided by 3 factorial plus j exponent 4 is equal to 1. So 1 times theta exponent 4 is the same as theta exponent 4. So we have this divided by 4 factorial plus j exponent 5 is equal to j. So plus j theta exponent 5 divided by 5 factorial, and so on and so forth. Now at this point, we have real values and imaginary values. So we are going to group them as such. We are going to group them into real and imaginary values. So for the real values, we have 1 minus theta 2 over 2 factorial plus theta 4 over 4 factorial, and so on and so forth. So these are the real values, and the imaginary values are the values we have j attached to them. So we can factor out j. So we have plus j. Now the first imaginary value is j theta. So we have theta, and then we move on to minus theta cube divided by 3 factorial plus theta 5 divided by 5 factorial, and so on and so forth. Therefore, we say that this is equal to cos theta plus j sine theta. Therefore, e exponent j theta is equal to cos theta plus j sine theta. Now let's call this equation 2. So what happens when theta is negative? So when theta is equal to negative theta, that is when we have a negative angle, then e exponent j theta, that is from equation 2, we have cos theta plus j sine theta. So we are going to substitute negative theta in place of theta. So that's going to be e exponent j times negative theta is equal to cos negative theta plus j sine negative theta. Now let's simplify. So we have e exponent negative j theta equals, now cos is an even function, therefore cos negative theta is the same as cos theta. However, sine is an odd function, so sine negative theta is the same as negative sine theta. So we have negative j sine theta. So this is the equation you are going to use when theta is negative. So in that case, the polar form of a complex number, that is written as z equals r into brackets cos theta plus j sine theta, which can be simplified as r polar theta. So that is the polar form, can now be expressed in exponential form as z equals r times e exponent j theta, that is from equation 2. So we have r times e exponent j theta. So this is the exponential form. So in summary, a complex number can be expressed in 3 different ways. We have the first one to be the rectangular form, that is of the form x plus jy. So we call this the rectangular form, rectangular or the Cartesian form. And secondly, we can have the polar form, and lastly, we can represent a complex number in the exponential form as r times e exponent j theta. So this is the exponential form. And notice that in the exponential form, the value of theta is always in radians. So for example, if you are given the complex number 5 polar 30, and this is in the polar form. Now if you want to convert this to the exponential form, first of all you need to change this value from degrees to radians. So that is, we have 180 is equal to pi, therefore 30 degrees is equal to x. So we have x equals 30 times pi divided by 180. 30 goes into itself once, into 180 6 times. So we have x equals pi over 6. So this is the value of the angle in radians. Therefore, z equals 5 polar 30 becomes r. So we have 5 times e exponent j, and the value of theta in radians is pi over 6. So we have j pi over 6. So basically this is how to do the conversion from polar form to exponential form. Now let's take some examples on how to find the end roots of complex numbers. So let's take our first example. Find the roots of z square equals 1. Find the roots of z square equals 1. Let's solve this together. So from the question, we are going to find the roots of z square equals 1. Now z square is a complex number, just that it has no imaginary value. So we can express this as 1 plus j0. Okay, we can express this as 1 plus j0. Similarly, from this equation, we can express this as z squared minus 1 equals 0. Now this tells us how many solutions or how many roots we are going to obtain. So since we have z to the power 2, we are going to obtain 2 roots or 2 solutions. So how do we obtain these 2 roots? First of all, let's represent this complex number in the Argand diagram. So we have this as the Argand diagram. We have the imaginary axis and the real axis, and O is the origin. Now we have the x component to be 1. So assuming that this is 1, we have the imaginary component or the y component to be 0. So basically we have the complex number lying on the positive x-axis. So this is the graphical representation of 1 plus j0. So 1 plus j0. So at this point, we are going to find the value of r, that is the modulus, and the angle theta or the argument. So we have r equals the square root of x squared plus y squared. We have the x component to be 1, so 1 square plus 0 square, and that is equal to square root of 1 is the same as 1. Therefore we have r equals 1. Now let's find the angle theta. So it is obvious that since this line is lying flat on the real axis, so the angle between the red line and the real axis is 0 degrees. Therefore we say that theta is equal to 0 degrees. So theta equals 0 degrees in radians is still 0. So we have 0 in radians. Now to find the roots of z squared, we are going to use the formula z exponent n is equal to r exponent 1 over n times e exponent j into bracket 2 pi k plus theta all over n, where the value of theta is in radians. K are positive integers starting from 0, and then we have n to be the number of roots. Now since we are supposed to obtain 2 roots, we are going to solve for z1 and z2. So for z1, k is equal to 0. We are going to use the values of k starting from 0. So for z1, we have k equals 0, and then we have n equals 2. And then for z2, we have k equals 1, and then still we have n equals 2. So let's find the roots z1 and z2. So for z1, still using this equation, z1 is equal to r exponent 1 over n. Now in this case, we have r to be 1. 1 exponent 1 over n, which is 2, times e exponent j into bracket 2 pi times k. We have k to be 0 plus theta in radians. Now in radians, we had the angle to be 0. So plus 0 all divided by n, which is 2. Now let's simplify this. So 1 exponent half is still 1. So we have 1 times e exponent j. So here we have 2 pi times 0, which is 0. So 0 plus 0 divided by 2 is still 0. And we know any non-zero number raised to the power 0 is equal to 1. Therefore, we have 1 times 1, which is equal to 1. Therefore, z1 is equal to 1. Now let's find the value of z2. So for z2, still using this same equation, z2 is equal to, we have r to be 1, and then we have exponent 1 over n, which is 2, times e exponent j into bracket, we have 2 pi times k. This time we have k to be 1. So 2 pi times 1 plus 0 radians. So that is 0 all divided by n, which is 2. 1 exponent half is still 1 times e exponent j into bracket. 2 pi times 1 is 2 pi plus 0, we still have 2 pi divided by 2, we are left with pi. So therefore we have z2 to be equal to e exponent j pi. So basically the two roots z1 and z2 have the same modulus, which is equal to 1. However, the difference between the two is their position. They are symmetrically spaced by 180 degrees. So we have the argument of z1 to be 0, while the argument of z2 is pi. So they are symmetrically spaced by 180 degrees. So the roots of a complex number are symmetrically spaced by 2 pi over n, where n is the number of roots. Now let's take the next example. So for example 2, find the roots of z cubed equals 1. So here, since we have z cubed, it means that we are going to obtain 3 roots. So z cubed can be expressed as 1 plus j0. So like we did in the previous example, let's represent this on the Gantt diagram. So we have the imaginary axis, we have the real axis, O is the origin. We have the x component to be 1 and the y component to be 0, which means that we have this going to lie on the positive x-axis or the real axis. So this is the complex number 1 plus j0. Next, we are going to find the values of r and then theta. So we have r equals the square root of x square plus y square. So that becomes 1 square plus 0 square, and that is equal to the square root of 1, and that is 1. So we have r equals 1. Now it is obvious that the value of theta is equal to 0 degrees, and we know that 0 degrees is the same as 0 in radians. So now using the formula, z exponent n equals r exponent 1 over n times e exponent j into bracket 2 pi k plus theta all over n. Always remember that the value of theta in this equation is in radians. So let's find the values of z1, z2 and z3. So for z1, we have k equals 0 and then we have n equals 3. So z1 is equal to, the value of r is 1. So we have 1 exponent 1 over 3 times e exponent j into bracket. We have 2 pi, k is 0. So we have 0 plus, we also have 0 in radians, all divided by n, which is 3. So this becomes 1 exponent 1 over 3 is the same as 1 times e exponent j. Now everything on top becomes 0, so 0 divided by 3 is still 0. So we can further simplify this as 1 times 1, which is 1. So we have z1 equals 1. Now for z2, we have k equals 1 and then we have n equals 3. z2 is equal to 1 exponent 1 over 3 times e exponent j into bracket. We have 2 pi, This time k is equal to 1, so 1 plus, we still maintain 0 because the angle is 0 in radians, so divided by 3. So this still remains as 1 times e exponent j into bracket 2 pi times 1 is 2 pi plus 0 is still 2 pi divided by 3, so that is 2 pi over 3. So we have z2 to be equal to e exponent j into bracket 2 pi over 3. Now let's find the value of z3. So for z3, we have k equals 2 and then we have n equals 3. z3 is equal to 1 exponent 1 over 3 times e exponent j into bracket, we have 2 pi, k is 2, so 2 plus 0 all divided by 3. Let's simplify. 1 exponent 1 over 3 is still 1 times e exponent j into bracket 2 pi times 2 is 4 pi divided by 3, we have 4 pi on 3. So finally we have the value of z3 to be e exponent j times 4 pi on 3. So you realize here that always the value of the modulus for all the 3 roots are the same, except that they are symmetrically spaced by 2 pi over n. This time we have n to be 3, so that is 2 pi over 3. So the first one has an angle of 0 radians. The second one will have an angle of 0 plus 2 pi over 3, so that is 2 pi over 3. And the third one will have 2 pi over 3 plus 2 pi over 3, and that is 4 pi over 3. Now let's try this example. Example 3. Find the cubic roots of z equals -1 plus I. Now because we are going to find the cubic roots, we are going to obtain 3 different roots. So we can express this as z cubed equals -1 plus I, like what we had in the previous examples. You can also write z equals the cube root of -1 plus I. Any of them is correct. Now let's focus on the question we have. Z equals -1 plus I, that is to find the cube roots of z. So we have z equals -1 plus I. So on the Argand diagram, we have the imaginary axis, real axis. This is the origin. So the x component is -1. Let's assume that this is -1. The y component, we have 1. So this is 1. So we have z to be -1 plus I. Now the angle between r and the negative x-axis, let's call this alpha. Notice that we are interested in the angle theta, that is the angle r makes with the positive x-axis, that is the angle theta. Now let's find the values of r and theta. So we have r to be equal to the square root of x squared plus y squared. So that is equal to the square root of -1 squared plus 1 squared. So that becomes 1 plus 1, the square root of 2. So we have r to be equal to square root of 2. Now let's find the value of the angle theta. So to do so, we need to first of all find the angle alpha. So alpha is equal to tan inverse of the absolute value of y divided by that of x. So this is equal to tan inverse of 1 over 1, and that is equal to 45 degrees. Therefore, we have alpha to be 45 degrees. Now, if alpha is 45 degrees, now the full angle between the positive x-axis and the negative x-axis is 180 degrees. So if we want from this point through to this point, then we want to subtract the angle alpha from 180 to get the value of theta. Therefore, we have the angle theta to be 180 minus 45, and that is equal to 135 degrees. Now let's convert this value from degrees to radians. So in radians, pi is equal to 180 degrees. So what is equal to 135 degrees? So basically we have x equals 135 times pi divided by 180. So 45 goes here 3 times, 45 goes here 4 times. So we have x equals 3 pi on 4. So this is the value of the angle in radians. Now, since we have the value of r and the value of the angle, we can find the 3 roots of this complex number. So using the equation z exponent n equals r exponent 1 over n times e exponent j into bracket 2 pi k plus theta over n. Now let's find z1, z2, and z3. So for z1, k is equal to 0 and then n is equal to 3. So z1 is equal to, we have r to be the square root of 2. So the square root of 2 exponent 1 over 3. Now this becomes 2 exponent 1 over 2 times 1 over 3, which is equal to 2 exponent 1 over 6. So we are going to write down 2 exponent 1 over 6. So z1 equals 2 exponent 1 over 6 times e exponent j into bracket. We have 2 pi times 0. So 2 pi times 0 plus, we have the angle in radians to be 3 pi on 4. So 3 pi on 4 all over 3. So let's simplify this. We have z1 equals 2 exponent 1 over 6 times e exponent j into bracket. 2 pi times 0 is 0. So plus 3 pi on 4. We still have 3 pi on 4 divided by 3. So we are going to multiply by 1 over 3. That is the reciprocal of 3. 3 cancels out 3. We are left with pi on 4. So we can simplify this as pi on 4. So finally, we have z1 to be 2 exponent 1 over 6 times e exponent j pi on 4. Now let's solve for z2. So for z2, k is equal to 1, n still remains 3. Don't forget that we've already catered for the square root of 2 exponent 1 over 3. Therefore, we are still going to maintain 2 exponent 1 over 6. So we have 2 exponent 1 over 6 times e exponent j. Inside of the bracket, we have 2 pi. This time k is 1 plus the angle in radians 3 pi on 4 all divided by 3. So this becomes 2 exponent 1 over 6 times e exponent j into bracket. Now let's work this one out. So we have 2 pi times 1, which is the same as 2 pi plus 3 pi on 4. Now instead of writing 2 pi, we want to make the denominators the same so that we can just add the values at the numerator. So instead of writing 2 pi, we are going to write 8 pi on 4. Now it is the same as 2 pi. So 8 pi on 4 plus 3 pi on 4 is 11 pi on 4. So this becomes 11 pi on 4 and then divided by 3. So we can multiply by the reciprocal, which is 1 over 3. And this becomes 11 pi on 12. So that is the angle, 11 pi on 12. So finally, we have Z2 equals 2 exponent 1 over 6 times E exponent J 11 pi on 12. Now let's find the value of Z3. So for Z3, K is equal to 2, N is still 3. Z3 equals 2 exponent 1 over 6 times E exponent J into bracket 2 pi times 2 plus 3 pi on 4, all divided by 3. Now let's simplify. We have 2 exponent 1 over 6 times E exponent J into bracket 2 pi times 2 is 4 pi. So this time we have 4 pi plus 3 pi on 4. So we can express 4 pi as 16 pi on 4. I mean, when you divide through, you still arrive at 4 pi. So 16 pi plus 3 pi is 19 pi. So we have 19 pi divided by 4. So 19 pi divided by 4 divided by 3. That becomes 19 pi divided by 4 times 1 over 3. This becomes 19 pi over 12. So we have 19 pi divided by 12. So finally we have Z3 to be 2 exponent 1 over 6 times E to the power J into bracket 19 pi on 12. So these are the values of Z1, Z2 and Z3. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.